Hi everyone, my name is Lin Nguyen and I am a PhD candidate at the University of Illinois Urbana-Champaign. In this video, I will summarize the main result from my paper, the AGORA Galaxy Simulation Comparison Project, paper 9, part 1, focusing on studying the effects of a major galaxy mergers on star formations of a Milky Way-mass Galaxy Progenitor. And I want to thank my collaborators in the Agora collaboration for helping me leading this project. A little bit about the Agora collaboration. So the Agora collaboration is the multi-institutional and international collaboration focusing on comparing different galaxy simulation codes to understand each code better and to help enhance the predictive power of simulations in studying galaxy evolutions. One of the main results of the Agora collaboration is the Cosmorun high-resolution zoom-in cosmological simulations. In the Cosmorun suite, we have currently 9 codes, which share the same initial conditions, mass resolution, star formation prescription, cooling, heating, solver, UV background, and analysis tool, to name a few. The two main differences among the codes is the hydrodynamic solver, whether it's mesh-based or particle-based or hybrid, and the stellar feedback implementation, which follow the common practice in each code community. This graph here shows the list of paper that the Agora collaboration have been produced, and this paper is paper 9, focusing on studying the effect of major mergers. This project is split into two parts, part 1 and part 2, and we will talk about the part 1 in the series, which focus on star formations. So here I show the galaxy mergers that we investigate. So this is a major mergers, and first we tracked the distance between the two galaxies, and from the distance plot here, we can identify key timings of the mergers, including the start of the mergers, which is when the two halos start to overlap, the apophysis time step, and the coalescence time step. And with these key time steps, we can divide the merger process into 4 main stages, as shown here, in order to help study the mergers easier. One of the main result of the paper is that we find that the pattern of the star formation rate evolution during the merger varies systematically depending on the types of stellar feedback employed in each code. So among the 9 codes that we have here, each of them use a different stellar feedback scheme, but we can group them into the general type. We have codes that use kinetic feedback in addition to thermal feedback and something else. Those codes are ART1, Garchard 3, Garchard 4, and Gizmo. We have codes that use only thermal feedback, which are Enzos and a Rebel T. And we have codes that use the radiation pressure, which is ART1, or delay cooling, which is marked by the asterisk symbol. So Ramses, Gear, and Gadget 3 use delay cooling. And last but not least, Chang'e with the dagger symbol use the super bubble. So we find that for codes that use kinetic feedback in the scheme, the star formation rate peak in one long prolonged starburst starting from the first passage stage and then peak and then start to decrease in the later half of the coalescence and post-coalescence stage. And we see the same pattern in oaths for code that use kinetic feedback in their stellar feedback scheme. On the other hand, we find that codes without the kinetic feedback, or coat use thermal feedback and something else without kinetic feedback. The star formation rate increase more gradually and continuously throughout the interaction and even into the post-coalescence stage, as seen here in these five codes. And last but not least, we find that for codes that use the delay cooling or radiation pressure in their scheme, the star formation rate is more bursty and jumpier with more small amplitude fluctuations on short time scale between consecutive time steps, as seen here in these four codes. So in order to better understand the star formation rate pattern during the mergers, we look at the gas properties. So in these two plots, we shows the gas phase plot between the gas temperature and gas density on the left column here. And on the right column, we show the distribution between the distance of the gas element to the galactic center and the gas density. And each row shows a different stage. So we have the start of the mergers, the end of the info stage, the time step of the first apoapsis, and the time step in the coalescence or post-coalescence stage. So we find that for codes using kinetic feedback, which are the four codes here, we find that by the end of the first passage stage, so around on the third row, set between second and third row here, we find a larger amount of gas collapsing to the galactic center and form a very high central density with low gas temperature, and this explain an earlier starburst that we see in the Ford code. On the other hand, for codes that implement only thermal feedback and nothing else, for example, Enzo and the Repo T, we see the gas collapse to the galactic center behavior only in the coalescence or post-coalescence stage. For example, here you only see that gas reach high central density and low temperature primarily during the coalescence stage, which is later compared to code using kinetic feedback, and that's explained why the star formation rate increased more continuously into the post-coalescence stage for these code. Last but not least, we also find that for code using delay cooling or super bubble feedback, these two feedback schemes efficiently prevent gas cooling, and this result in a broader gas distributions and prevent gas from collapsing to form a very dense central density, as you can see here. Another main result of the paper is that we introduce a new method to calculate the burst fraction or the star formation rate enhancement for galaxy mergers without relying on a control sample. And using this to find the burst fraction, we also find a correlation or negative correlation between the burst fractions and the gas fractions of the pre-mergers gas fraction of the system, where a system with a higher gas fraction result in a lower burst or lower star formation enhancement, and this result is consistent to what is found on in the literature. We also find a relatively weak correlation between the burst fractions and the merger total mass ratio. So thank you very much for your attention, and please refer to the paper for more details on the project or reach out to my email. Thank you.